done with chapter 7 stuff. We're on to chapter 8 stuff. So in any case, here's your homework for those who have been following along in the book and trying to do it out of the book instead of doing it on WebAssign. There is one little note here, which is that your book, I don't think, quite gives you the equation it was supposed to for one of these problems, the applying your knowledge problem. That problem, by the way, is not on the online homework, so if you're trying to do everything, you might do that one too. But the equation you're supposed to be obtaining is this one right here. The equivalent resistance is the product of the two resistors divided by the sum of the two resistances. And that's stuff that we'll look at in part 2 of this lecture set. Part 1, we just want to look at charges, forces, fields, that kind of thing. I'm not going to do a review quiz today since it's Good Friday and people might actually have a legitimate reason to not be here for once. So let's look at electric charge, electric force, and so on. Electric charge is one of those fundamental quantities. In fact, it's one of the base quantities that I showed you way back in the first chapter. We usually like to use a lowercase or uppercase q to represent charge. And in a more detailed class, the basic difference is that usually we use a lowercase q if it is a single point charge, like a one charged particle, like an electron, or even if it's like a nucleus or something like that, some small point-like object, then usually we use this. And if it's an actual charge distribution, then usually we'll use a big Q. And so charge distribution would be like if you had a comb or something and you brush it for your hair a bunch and it picks up some static charge to it. That charge is sort of distributed over the comb. And so that one would be your distributed charge. What we want to look at mostly is how forces interact between, or how different charged particles interact via forces. And then in the second lecture set, we look, or in the second part of this lecture set, we look at movement of charges, which is called current. And we'll look at basic circuits, that kind of thing. And then in the third part, we'll look at magnetic fields and a few applications such as motors and generators and transformers. Charges come in two types. We usually represent them as positive and negative. Basically, how we know this is because you can charge up an object and you can find that in some cases it will attract other charged objects and in some cases it will repel other objects. And so the basic conclusion that comes out of that is that if they have like charges, they'll attract each other. If they have like charges, they'll repel each other. If they have unlike charges, they'll attract each other. So on a microscopic level, an atom might have a nucleus, which is basically positively charged, and then it might have some electrons orbiting the nucleus. Those are negatively charged. The old classical model for the orbit basically just has this electron moving around the nucleus in more or less a circular orbit. It turns out that that's not a very accurate model in the light of quantum mechanics. The electrons actually kind of have what's called the distribution cloud that they inhibit, or that they inhabit. They're sort of there's like a probability of finding the electron at any given point in space. In general, the common particles that you find for an atom are electrons, protons, and neutrons. And what's here is a little table that shows the symbol that we often will use for them. So an electron will use an E- because it's negatively charged. And then we have an approximate value of the charge. Note that that's only an approximate value. The actual value has additional digits to it. And then we also have an approximate value for the mass. Again, it's only an approximate value. And we've done the same thing with the proton and with the neutron. And so what you should notice here is that proton and electron have the same magnitude of charge, but different signs. So it's plus 1.6 times 10 to the minus 19 coulombs for a proton, minus 1.6 times 10 to the minus 19 coulombs for an electron. Coulomb, therefore, is the basic unit of charge. And we'll see who it's named after a little later today. Neutrons have no charge to them. You can also see what the masses are for them, and you may notice if you look closely that if you add the proton mass and the electron mass, you end up with very nearly, though not quite, the neutron mass. So the neutron is just a little bit bigger than the proton, and both are a lot bigger than the electron, and it turns out that the difference between them is also a little bigger than the electron. This is important in some sorts of nuclear physics. There's a decay process called the beta decay, in which essentially a neutron will decay into a proton and an electron and then some energy in the electron by converting some of the mass, some of the extra mass into kinetic energy. So you have a moving electron. So this unit of charge, the Coulomb, is named after a guy who studied basically how much force exists between charged particles. So Charles Coulomb. And it's a very small quantity for a single electron or a single proton. You may wonder, why is it that electrons and protons have such small quantities of charge if they're the basic charge carriers? The answer is because you had to measure this stuff in the lab at some point first. The way that a Coulomb is actually defined is it's defined by how much force per unit length exists between a pair of wires that are carrying some current. And you have to have a big enough amount of force to actually measure it. Therefore, you have to have enough charge to measure that, and that ends up being quite a few electrons and quite a few protons. As far as how do electrons or protons or any other point objects, point charges, interact, we use what's called Coulomb's law. And Coulomb's law basically makes use of a bunch of observations, some of which are by Coulomb himself, others of which have been kind of known before. And he sort of synthesized them into a single equation that takes everything else into account. One of the things is this fact of like charges repelling and opposite charges attracting. But there's actually more to it than that. It turns out that how strongly they attract depends on how much charge each one carries, and it depends on how far apart they are. And so you can find that the force between some charges is inversely proportional to the distance between the two charges squared, and it's proportional to the two charges products. There should be a proportionality. All right, and so in order to make it an equality, you have to know what the proportionality constant is, and that's what's called Coulomb's constant. So to make it equal, we have to multiply it by some constant. It's usually abbreviated with a K, sometimes a K sub E, or a K sub Q, or a K sub C. I'll just use a K. So to draw it, you have one charge here, you have one charge here. They are some distance r apart. The sign of this thing tells us whether it's attractive or repulsive. So if you have a negative sign for the charge, it's essentially, or for the force, it's essentially attractive. If you have a positive sign, it's essentially repulsive. It means they push away instead of pulling together. So how do you get each of those two signs? How would you get a negative sign for this collective? Well, r is a real number and you're squaring it, so that's always positive. The Coulomb's constant is just some number. It's also positive. It's about 9 times 10 to the 9 for what it's worth in units of newtons times meters squared per Coulomb squared. So what determines the sign of this is basically the signs of these two things. So if you have a positive charge and a positive charge, then the two multiply together, you get a positive sign. That's repulsive. If it's negative and negative, then you multiply them together. Two negatives multiplied together, it also gives you a positive, also repel each other. But if one is negative, one is positive, you multiply those together, you get a negative overall sign. That's attractive. All right. So here is the equation written out for you. Constant times charge 1 times charge 2 divided by the distance between the two charges squared. And it shows an approximate value of the Coulomb constant, 9.0 times 10 to the 9 Newton meters squared per Coulomb squared. Again, the exact value is quite a bit longer, like quite a bit more significant figures. It's actually like an 8.99 something. But for our purposes, 2 significant figures is adequate. There are a few worked examples in the online videos. This one has the picture of a couple of Van de Graaff generators. We actually have a smaller one of those. Those ones there are big enough that they would make sort of like a lightning in the room when they're being operated. So how do you charge an object? There's a few ways, and it depends upon what kind of object you have. If the object is an electrical insulator, in other words, it doesn't conduct electricity very well, then usually you charge it by some version of rubbing on it. Like a comb you can rub through your hair, and it will charge. Or if you're wearing shoes with the wrong kind of soles or the right kind of soles, depending on your personality type, you shuffle across the floor at the grocery store or whatever, and you pick up a lot of charge from that. Then you shock yourself or somebody else the first time you touch something. Okay. This one just shows a picture with rubber versus glass rods. It turns out that depending on the material you have, rubbing it might give it a positive charge or might tend to give it a negative charge. So rubber tends to pick up negative charges. Glass tends to pick up positive charges. And so if you actually took a glass rod and rubbed it, took a rubber rod and rubbed it, you'd find that the two try to attract to each other. But if you have two rubber rods or two glass rods, they'll tend to repel. There's two ways, before I get into back to Coulomb's law, there's two ways that you can charge a conductor. So all those things I showed you are good for charging insulators. Conductors you charge either by contact or by induction. Contact charge basically means you have one charged object, you have your conductor, you bring them into contact with each other, and some charges leap across or leap away from the conductor. You pull them apart, the conductor is now charged. That one basically tends to work by, if you have a positively charged object and you touch it to the conductor, you're going to tend to have a positively charged conductor. If it's negatively charged, then you'll get a negatively charged conductor. The other way that you can charge, though, is by induction. And that's the way that one works is basically you have, let's say, two objects. Maybe this one is already charged and could be a conductor, could be an insulator. It just has to have a charge distribution somehow. So maybe this one right here is an insulator. You've put a bunch of charges here on this part of it. Maybe it's like a comb or something, and you combed your hair, and now it's somehow a glass comb, and so it has a positive charge. Or it could be a rubber one, and then it has a negative charge. In any case, you've got a bunch of positive charge here. This one right here is a conductor. It means any charges, well, it means many of the charges in it can move around freely. So positive charges tend to attract other positive charges, attract negative charges and repel other positive charges. So what you do is you connect this thing to ground somehow. For example, you plug it into the grounding socket in your wall, or you literally attach it to the ground, or what have you. What happens is negative charges will tend to want to move like this. So you get some negative charges on it that have been sort of attracted closer to where all these positive charges are. Then you take away the grounding wire. So you unplug it or you remove the wire, what have you. Now there's nowhere for these negative charges to go except for elsewhere in the conductor. So if you take this thing away now, what happens is these negative charges will basically just spread out around the surface of your conductor, like so. So now you have a negatively charged conductor. That's called charging by induction. All right, so on to Coulomb's law, or back to Coulomb's law. If you are attentive and have a certain acuity for equations, you may have noticed this already, which is that the force for Newton's law of universal gravitation and the law for forces with Coulomb's law with charges have the same basic form. In both cases, you have force is equal to some constant, could be G or could be K, times some product, mass 1 or mass 2, or charge 1 and charge 2, divided by a distance squared between the two. And the main differences are, for Newton's law with gravitation, you use the gravity constant. For Coulomb's law, you use the Coulomb's constant. For gravity, you use mass, which happens to be the thing that is sort of interacts with the gravity field. For Coulomb's law, you use the charges, which is the thing that produces and interacts with an electric field. All right, so this means that all the math that you practiced on Newton's law back in chapter 3, Newton's law of universal gravitation, all the math you did there is the same math as you use here, with the one exception being that you change what the constant is and that you pay attention to charge rather than to mass. And now you have to pay attention to, is there a sign or not? It turns out that electric charges are a lot stronger than gravitational. But force from electric charge is stronger than force from gravity. And to see that, we can pop back to this chart that I showed you a little bit ago. Whoops, this one. And we can calculate how much gravitational attraction is there and how much electric attraction is there, electrostatic attraction is there, between an electron and a proton. Now we're going to get small numbers in both cases because there's not very much mass and there's also not very much charge. But how small of a number are we going to get? So let's look. So gravitation. We need to pick some distance to put them apart. Maybe we'll pick 1 nanometer. Nice round number, very small, a bit larger than what's called the Bohr radius, which is essentially the radius of orbit for one of the old models of the atom. So let R be 1 nanometer. This one right here, your value for G is 6.67, or really it's negative 6.67, times 10 to the power of minus, does anybody remember? Too long ago? So like a minus 11. Then we have to use the mass of these two things. So for an electron, get 9.11 times 10 to the minus 31 kilograms. For a proton, 1.673 times 10 to the minus 27 kilograms. And then divided by r squared, but r is given in nanometers. So that's 1.0 nanometers, but we got to convert it to meters. So times 10 to the minus 9 meters per nanometer, and then square it. So this is now basically a calculator problem. So we pull the calculator out, we start typing some numbers in. 6.67. That one's 9.11. That one's 1.673. So we end up with force of gravity. It's about 1.01. So 1.0 times 10 to the, let's see, we have 2. Minus 11, minus 31, minus 27, plus 9. Plus 9 again. So let's see, 58 minus this. Very small number. Now we can repeat, but for the Coulomb, just for the sake of comparison. So this one was Newtonian. So this one says the force between the two charges should be K, Q1, Q2 over R squared. So those are your charges. We need 9.0 times 10 to the plus 9 Newton times meters squared per Coulomb squared. And then we have minus 1.60 times 10 to the minus 19 coulombs, and plus 1.60 times 10 to the minus 19 coulombs. Divided by R squared. R, again, is your 1 nanometer. So again, calculator problem. We have 9 times 10 to the 9. We have 1.6 times 10 to the minus 19. We have 1.6 times 10 to the minus 19. So this looks like about 2.3. So 9, 10, 8, 29. Whoops. Calculator gave me an error. Gotta start over. Says times 10 to the minus 10 newtons. There we go. So again, that looks like a really small number. But notice this one's times 10 to the minus 10, this one's times 10 to the minus 49. So it's a seemingly small number, but in comparison to gravity, 39 orders of magnitude larger. So we're talking, given that this is a 1 and this is a 2.3, we're talking a 23 followed by 38 zeros times bigger than gravity. for this particular electron and proton pair. That's pretty substantial. So why is it that gravity seems to be the dominant force of the universe on a large scale? Why gravity and not the Coulombic force? By the way, this one is via video, uses a slightly different radius, so if you want to compare and contrast, it's the same math, we really only change out this number right here to the actual Bohr radius. So why is it that gravity is the dominant force on large-scale objects if this is so clearly smaller than this on small-scale objects? Any thoughts? None? The simple answer is because we have about an equal number of positive and negative charges in any one object, and charges can shield each other. Which means if you have, say, a +1 and a -1 and a +1 like this, this one could be shielding these two from each other and vice versa. So you end up with effectively no net force on this one from these two. And each of these two actually have an attractive force to this one. And if you tweak the numbers a bit, then you can set it up so that the whole system is balanced. There's no net force on anything. Okay, but with gravity, you can't do that. You just add more gravity, that just means there will be more force. So because large-scale objects are more or less neutrally charged, you get more or less zero force. But for gravity, there's still force present. You can also look at how much Coulombic force is present between a neutron and an electron, or between a neutron and a proton. And what you'll find is that there's no force present because the neutron has no charge. So all the force that could be present is from gravity. So on a large scale, if you have an atom that has an electron and a proton on it, your atom is maybe like this. And then the next atom over might be, say, here. And so on. What you end up getting is that as far as this atom and this atom are concerned, there is a little bit of electrostatic force, but then once you get to an atom over here, there really isn't much electrostatic force left between this one and this one. They're just too far apart compared to the spacing between plus and minus charge. But as far as gravity is concerned, there's still some force present. This slide right here talks about the electric field. So certain types of forces are what we call field forces. Gravity, by the way, is a field force as well. That's why from time to time I will mention that there's a gravity field. At least in Newtonian mechanics, it's a field force. The electric force also is field force. And you can draw the field lines from a given charge. What they basically do is they show if you were to place another charge somewhere in space, what direction would the force act on that charge? Assuming it's a positive charge, by the way. So the top one there just is a single positive charge. The field lines radiate out from it. If you place another charge somewhere in space nearby that is positive, it basically is being pushed away. But if you have multiple charges like this, then placing another charged particle somewhere in space might mean it does something other than just be pushed away. So for example, here, you place your positive charge here, it actually kind of gets drawn inward towards the negative charge. Over here, it gets pushed outward away from the charge pair. In here, it tends to be accelerated like this. Now, if it's initially at rest, it won't, or moving, it won't necessarily follow the field lines, but they give you the direction that the force will act on it. Down here, you have a pair of charged particles that are same sign of charge. And so in most locations that you can place a positive test charge, it's going to be pushed away. But it turns out that if you put it right here, right between the two of them, then there's no force on it. It's being pushed this way, and so the net amount of force is 0. So one of the things that the field lines can do for you is the denser they are in a region of space, the stronger the amount of force that will be present on a given test charge. It means the stronger the electric field. The sparser they are in some region of space, the weaker the amount of force. So right here, they're very sparse, and therefore it's a very weak amount of force, even though it may be really close to the two charges. Over here, they're a little more dense, and so there's a lot more force. Here, they're very dense, and so there's more force, and so on. So that brings us to the end of the first part of all of this, which is on charges, forces, and fields. Are there any questions? All right. Well, next time we'll pick up with Ohm's law and current and circuits. I'll give you a little bit of a preview of what it looks like in case we have to go fairly quickly. The basic things that we consider for next time are energy, and also movement of charges. Energy, we basically use voltage. And so the energy for a system is the voltage, or sometimes called electric potential, times the charge. We represent this as U equals Q times V for voltage. Movement of charge gives us current, which we use an I to represent for whatever reason. That's how much charge has moved through a location in space per unit time. And what we're going to see is that you can combine these two things into what's called Ohm's law. Ohm's law says that the voltage drop across an element in a circuit is equal to the current through the element times the resistance of the element. The resistance is resistance to current flow. And I think we'll stop there.